Hello everybody! I hope everyone's having a wonderful day. We're going to be doing another property of big O today. So, namely what I'm going to be doing is imagine if I gave you two complexity functions. And I know both have the same result in terms of big O. So they have the same order. And this other order is written in terms of another complexity function called H. What I'm going to tell you is that if you sum over F and G, this will also be big O of H. So written in more careful language, if F is big O of H and G is big O of H, then the sum F plus G is in fact big O of H. So just as a quick picture, just to really give you an idea of what I'm talking about. So imagine I have right here, this is big O of H. This is the set of all complexity functions for which they are big O of H. So we know that F is somewhere in big O of H here. We know G is also in big O of H. All I'm saying is that if you take a composite of these two, so if I took F plus G here, it's sitting in here. It's not outside of big O of H. It's indeed a member of big O of H. So that's what we're going to be proving here. So let's try proving this claim. What's the first thing we should probably do? Let's first read the statement and make sure we understand it. So first, we know that we're given that F is big O of H and that G is big O of H. We have these two facts. Now remember, like I said at the beginning of this section, if you're given information at the beginning, that might be very helpful for actually proving the claim. So because my statement actually involves the sum of these two functions here, F and G, and they both relate to H. So probably there's something I need to do with those two. So why don't we first start off by writing out what the definition of big O means for each one of these two statements that I'm given. So let me first write down a game plan of what we're going to do, because we always need to know what we're going to do. It's usually a good idea to write this down for the reader. To prove the claim, we determine constants C, which remember C is a positive real number, and N0, which is of course a positive integer. Remember, it's a positive integer. Positive integer, such that for all n greater or equal to N0, what are we going to need to prove? We need to prove that F of n plus G of n is less than or equal to C times H of n. So now what I'm going to do next is I'm going to just write down what each of these two statements over here that I have a composite of these two things, because I have both of these statements that are, I could just assume to be true. If I know that they're true, if I could deduce from these two things that, then we're done. So all I'm going to do is write out what these two things mean, then I'm going to see if I can write something meaningful combining those two things, what those definitions mean. So both F is big O of H and G is big O of H, implying the what? What does that imply? What does that imply? What does that imply? So if I know that this and this are true, that means that this one, there indeed exists constants, right? There exist constants. You can call them, for example, this is C1, and we can call this N1. C1 and N1. I know that these exist. There exists these two constants. In addition here, I know that there exist two constants. I'm going to just write this down. I'm going to kind of compose it into one sentence. You don't have to do it this way. You can write it in two separate sentences. Sometimes it's helpful to do it this way, but you don't have to, of course. implying, so what does it imply? There exists constants C1, C2, which are both positive real numbers, and N1, N2, which are positive integers, such that the following is true. So let's move over to the other board. Okay. So anyways, now what we're going to do is we're going to write what those inequalities would mean for each one of those big O definition invocations. When I invoke the definition of big O. So we know that f of n is less than or equal to c1 times h of n. And this is for all what? It's n greater or equal to n1. And g of n is less than or equal to c2 times h of n for all n greater or equal to n2. Now I'm going to use the same strategy I just did for my previous property that I approved. Now that I have two inequalities here, do you see something I can do to combine them in some way such that I have a sum that's f of n plus g of n? Do you see what I can do here? I have two inequalities. I want you to think about the buckets that I used to use when we first started talking about summing over inequalities in some of my earliest examples with everybody here. What did I do? Well, I showed that the left-hand side is less than or equal to everything on the right-hand side. But I do that for each one of my buckets, then I put and lump it all together, right? I'm going to do the same thing here. By summing over both of the above inequalities. That cue's dying. We need to fix that. By summing over both of the above inequalities, when n is greater or equal to the max of n1 and n2, because I want to make sure that I don't make a statement about n that's too small. So we have to be very careful here. So I'm going to make sure that I'm making sure these inequalities both hold at the same time, as long as I make sure that n is large enough. That's why I'm doing this. So what does that mean? So I get f of n plus g of n. So I'm summing over both of these inequalities. This is less than or equal to, so what's this less than or equal to? C1 times h of n, right? C1 times h of n. To make it a little easier to see, I'm going to put parentheses around that. Plus, now what's this less than or equal to? So what's g of n less than or equal to? It's less than or equal to c2 times h of n. So I'm going to use parentheses again to really emphasize that I'm invoking these two separate inequalities and I'm adding them together. Now, there's something interesting here. Something interesting. I have two h of n's here, right? That means I can factor out something, right? But what can I factor out? I could factor out these two constants here, like this. C1 plus C2 times h of n. Do you see what I should pick for C yet? Do you see what C should be? It's sitting right there. Now remember, I can't assume what F and G and H are. But I have this right here. Maybe you should select this to be C right here. What should N0 be? What's N0? Well, this whole works when N is at least this big. So maybe I should pick N0 to be that. By selecting constants, C equal to C1 plus C2 and n0 equal to the max of n1 and n2, the inequality f of n plus g of n is less or equal to c times h of n holds for what? It holds for all n greater or equal to n0. So this just summarizes everything all in a nice big bow. So we're all done. Therefore, by the definition of big O, f of n plus g of n is big O of h of n. And we're done. So do you see how I'm showing you how multiple strategies that we've seen in the past actually serve as blueprints for these more general properties that I'm actually showing you here? So in addition, I also showed you a strategy that I used when I proved my previous property, and I used that here. You're going to see that this is going to be no surprise, and I'm going to be actually using it again. I'm going to be building on what I've done here, where I've combined two big O statements to make a new big O kind of statement. I'm going to do that next time when we do the next property for big O. So that being said, thank you very much, and have yourself a beautiful day. I'll see you later.